Testing.
I just knew it was twice the size, so I just looked at it.
I used the twice one, and I was like, kind of same thing, because if you're looking at the bigger one.
Yeah, it
Right.
didn't say which one, but you know.
Because I actually went online and took that test, and I wrote her an email with those. I found that one and the other one that said A and C was
The Brenner.
yeah.
question C was A and C.
Yeah.
So yeah, I thought, well, maybe she'll get a chance to fix those, but.
Oh, I need to dump it to a student supervisor on that one, just like, oh my god, like I use that for ADM, so she was symbolic therapy. I read it as what's false. And I don't even know how I did that, but I must have just, because I immediately passed off symbolic therapy. I'm like, how stupid. I hate when it's from me. Yeah, it's not excessively crazy.
I'd offer you a coat, but you already have one on. Well, there's also a blanket in the lab if you want. You can throw that over your shoulders. Yeah.
You think I should put this information back in that one case? This is just Jen's.
Just Jim's.
And
All right.
we are missing the second page in our thing. It's not in there. Well, I don't know, it's not really much to do about it. Awesome.
All righty. Okay, as we get settled in here and started, let's just briefly review what we went over yesterday, which was we're starting to get into some of the more complex stuff, so I want to make sure that you guys have a real strong foundation on this. We've taken our single crystal now and we've divided it up into many little crystals. The typical transducers we use in the labs have between 256, 512. Some of the newer transducers have as many as 4,000 little crystals within them. But in general, you could think of it as somewhere around 250 to 300 crystals that we're going to be using to form the image. And we use little wires attached to them to cause the electrical signal to hit the piezoelectric material and send out a little wavelet. And does anyone recall what the principle is that allows us to build these wavelets together? Huygens, right. Huygens. Huygens' principle allows us to build big waves out of little wavelets. Okay? And so if I take my transducer crystal and I use just a few of the crystals, I get a very narrow beam that comes out of it, and it focuses somewhere down here at this NZL or near zone length, and then it diverges afterwards. And that's what we expect to happen. And then what happens if I add more crystals to my firing? What's it going to do to the beam, Ivy? Yeah. So the near zone length will be farther, as you said, and the beam itself will be longer and have a deeper focus, is essentially what it has. Okay? And so what we're doing is we're truly controlling the diameter of the crystal by selecting more or fewer waves or wavelets to create these big waves. All right? So we're actually changing the diameter of the crystal by firing more or fewer. Now, we can also do a really nice thing. We can take these waves and we can adjust our timing of firing them. So instead of firing them all at once in big segments, we can change the timing of this so that, let's say I want my wave to come towards the left side of the screen here. Okay? I'll fire this one first. Okay, and we get a little wavelet from that. And then a little bit of time later, I'll fire this one. And so now this one is fired, and this one is still propagating out, and it's getting a little bigger. And then I'll wait a little longer, and I'll fire this one. Okay? And so now this one fires. This one is propagating out, getting a little bigger. And then the first one is even farther out and getting a little bigger. And then we fire this one a little later. And so this represents the early ones when it's drawn closer to the crystal. These are the later firings when they're farther away. All right? And what it represents is the electrical signal coming down the wire. So this one, the voltage is farther away, so it's going to take it longer to come down the wire. And we're going to end up with a wave coming out of this that basically has this structure, something like this. And the whole thing ends up kind of building together and moving in a direction. Yeah, so we're steering it electronically. And the easy way to look at this, if you ever see this on a registry exam, hint, hint, you can just draw a line across this, draw an arrow, and that'll tell you which way it's going, okay? These are going to build to make a big wave, so just draw your big wave in there, and you can draw an arrow perpendicular to the wavefront, and you know where it's going. You don't have to reconstruct it, but you can. And the wavefront is going to be moving in this direction if you have this type of timing on your firing. Okay? So then we can send our wave out this way. We can use reverse timing and send our wave in another direction if we want later. So we could go this way. And we can produce a picture from a standard flat transducer that encompasses a large area that way. Small footprint, large area, by using this electronic steering of the sound waves. Okay, so we covered that yesterday. This is how the sector scans are made today when we look at them. Typically, though, we use a different type of transducer, and so we'll take a look at how the curved ones form the image in just a minute. All right, so the other thing we can do is we can do beam focusing. We can actually focus this beam not with just the changing of the size of our crystal diameter, but we can focus it by changing our timing. Okay, so now we can electronically focus it, and if I fire out the two end crystals here first, okay, and we get little wavelets come out, and then we fire this one later, and this one later, and then these two will fire about the same time. Okay. I think I've got one too many crystals there. We'll make it an even number so that this makes a little more sense. Okay. And I told you that we can tell where the wavefront is just by drawing a wavefront across our timing, right? So now we've got a wavefront, you can see, is concave. And it's going to travel in this concave fashion into a point, right? So what's going to happen is instead of focusing, now you would expect a big wide crystal diameter like that to focus very deep, right? Ivy, that's what we had before. We had a wide crystal, you said, and it's going to focus deep. But if we change this wave pattern so that it's curved, what's going to happen is it's going to come in and focus very shallow. Okay? Just like that. It's going to, this curved pattern is going to cause the focusing to be very shallow, even though it's a wide crystal diameter. Does that make sense on why it does that? It's basically a big wave, and it's all moving into a point. All right? We normally think of a wave, if you drop a pebble into a pond, it spreads out. But if you take a large wave and you focus it at one point, all parts of the wave, and it's all traveling this way, then it's going to get to this point sooner. So now we've moved our natural focal zone, our NZL, from way down here up to here by changing the pattern of the firing of the crystals. All right? So now we can electronically change where we focus our beam, our sound beam. Not just by the diameter of the crystal, but also by the timing of it. All right, so what the manufacturers do is they take it one step farther and they actually will not only fire these off to steer the beam, but they will also focus it by firing them off in certain patterns, okay? So now I've got a beam that focuses, but it also kind of has a effect of driving the beam in this direction. All right, so we can change our timing pattern so that it steers it and focuses it at the same time, just kind of a combination of the two. Does that make sense to everyone? I see a few nods, yeah? Okay. And so that's what we're doing here. Electronic pulses can focus the beam to one spot. They can steer the beam, all right? And that allows us to change the shape and focal zones on our image basically at will, all right? All we have to worry about is where we want the focal zones put, and the machine basically takes care of the rest. They do want you to know how this works, okay? Little wavelets add together and create focused and coherent waves that go out and make images. And we're still only talking about transmitting beams into the patient, all right? So we're focusing them at a certain point, and we're learning to steer them electronically. I might get to annular arrays today if we have a chance. Those are crystals that are made. This is an annular array crystal that you see up on the PowerPoint, and it's just a series of concentric circles. Okay? We don't use those too much anymore, but there's usually at least one test on the exam on annular arrays. So I'll try to get into that if I have some time, but this is what an annular array is. It's a circular probe. All right. Does everyone feel comfortable with Huygens principle and steering wavelets?
I have a question.
Sure.
You just put in a image two focus zone. How do they do it when you want to have two?
That's a good question. How do they get the focal zone at two different points? And you literally, what you have to do is you have to send out two separate signals. Okay, so you send out one pulse that's focused here. So I send out one scan line that is focused right there. And then I send out another scan line steered in the same direction that is focused down here. Okay, so it requires two pulses to get two scan lines. So every time I add a focal zone, I'm adding another pulse to my image.
Now, is this done by the same crystal or is it a different row of crystals?
No, same crystal. And every time you send out a pulse, you have to sit and listen for the entire depth of your image. So if I'm down here imaging at 10 centimeters, even though I want this focus at 2 centimeters, I have to wait until it travels down here and back, which is 130 microseconds to get down there and back, before I send out this next pulse. And this one I have to wait till it goes 130 microseconds before sending out this pulse. So every time, it's just like creating a whole new scan line each time. Yeah. Every single time. So when you add, you might notice on the machines, if you're at clinicals, you add a whole, you can get like sometimes 8 focal zones on there. And it might feel like it's really, really slowing down. And it is, because you're basically adding 8 extra frames of information for every frame that you're acquiring.
And the reason why you add more is to see better at all depths?
Yes. You would add more because you want to see better at different depths. And things like pelvics, this is great technique because when you can sit there and you're breathing and the pelvis isn't moving a whole lot. If you're doing a liver, this may not work for you because people's livers are close to their hearts and there's a lot of motion up there, so there may be too much motion and our temporal resolution goes down too far to use a technique like this. But for things like pelvics and anything that holds still, if you're doing an elbow, this is great. You know, because there's not a lot of movement in an elbow unless they voluntarily move it. You know, so this originally was used in the pelvic imaging, and it turned out to be really nice for that. You know, great questions. Anything else we can clarify? Bless you. All right. So we can steer, we can focus electronically, we can focus by changing the crystal diameter. And what was that called when we have different sizes of crystals? Those are the aperture. Okay. So we can change the aperture of our crystal, which changes our focus. What would this curve look like? Okay. It would be focusing at some point, and you can see that it's steering because you have a preponderance of the wave moving in this direction, so it's being steered this way, and it's being focused at some point. So it would look something like that, the wavefront, and it's going to move down and focus at some point over in here. All right, and its general movement is going to be in this direction. All right. Okay. Okay. Yeah.
So the equation we have to figure the near zone with, like the frequency times the diameter squared, that's for a single crystal?
Yes, it is.
So these multiple crystals, is there any way to figure out the near zone? Because it can change all.
Right.
So there's no like formula.
Correct.
They can't ask you that question.
They won't ask you that question. They'll ask you that question on single crystal. Yep. All you can do is use that for a single flat crystal. Yep. Yep. That's true. With these, you just have to look at the timing patterns and kind of figure out where it's at. So with a timing pattern like that, Ivy asked the question, what was this shaped like? Well, they won't ask you what it's shaped like or exactly where it's focused because you don't have enough information to know that. But you do need to know that it is, the near zone has been moved closer and that it is being steered to basically the left as we look at this, as we look at the board. Okay. If we have a timing pattern that is all the same across there, okay, you would look at that and you'd go, okay, this is an unsteered, unfocused timing pattern. It's just all of them are being fired off at once. Okay, so if they asked you, you know, where is this beam going? It's going straight, and it has a natural focus, but it hasn't been electronically focused. Okay. So if it's a symmetrical, like that, then we have a timing pattern that is being focused but not steered. It's going straight and it's being focused. Okay? So we can look at the timing patterns and get an idea of where the beam is going, but you're not going to be able to sit there with a calculator and figure out exactly where it's focused or exactly where it's steered. We just get kind of a general idea about it. And I think that's all they want us to know, is that what is the general idea of where this beam is going. Okay, so I drew all of them so far. I've drawn all the timing patterns so that they're either steered to the left or focused. I should draw you one that's steered to the right just for completeness. And there you go. So you can draw your wavefront, draw a line perpendicular to that, and that's where it's going. All right. Okay. So Jennifer has joined us at home. Glad to have her there.
Again, it won't happen.
Hmm?
There's so many different ways it's not happening.
I
Okay.
was able to join, but it wouldn't let me hear.
Malka didn't have her desktop shared this morning, so yeah.
She didn't know.
Yeah, I don't know. I'll ask her about it. Okay, so let's talk about shaping the image shape, and so far what we've really been focusing on are sector scans, sector images, because this is what we initially started with the single crystal. By moving it back and forth, we were able to get a sector image. But we can get different shapes. The most common one that we work with in the lab today is the curved array transducer. And so what kind of a shape does a curved array transducer have, Stephen?
Concave.
Hmm?
Concave.
Okay, so right where it touches the patient, you have that concave top of the image, right? Okay. And then it fans out. Let me see here. We'll leave that on. Okay. So then it fans out in somewhat of a sector type image, right? And what does the far zone look like with those? Do you remember?
Yeah, it diverges.
Yeah, we've made it diverge. But the very bottom, is it usually flat across there? Yeah, it's the same shape, right? It just kind of is carried down. Okay. So that's your typical curved array transducer image. All right. And the beam is usually designed on these to pretty much fire straight off of perpendicular from the face of the transducer. And so that's its natural shape. Okay. Now, we know from what we just talked about with linear array flat crystals that we can steer them and focus them and do that. Can we do that with this concave curved array?
Maybe not as well.
That's a great answer, because that's exactly right. We can do it, but not quite as well as we can do with the linear array transducers. Yeah. So when we do the compound imaging, we actually use at least one scan line that comes straight off of the transducer, and then we use the timing to create other scan lines that are at angles. Okay? And we build those together into an image. So yeah, we can do that. Now let's take a linear array probe. What kind of image do we typically get with this type of probe, Angelina? What do we usually get with this? Just what kind of image do we get with just a linear array probe? What's the image look like on our screen?
Oh, straight, or you can change it to a vector.
Okay, so you're right. You're exactly right. So we usually get a straight box, and it can be either square or rectangular, depending on what we set our depth at. That's true. And normally, all the beams are fired down, straight down, and then they come back up, and we just get whatever's in here gets put in the box. And then she also mentioned sometimes you can have this where we'll make it a trapezoid. And so we have this trapezoid shape with these, okay? and we're opening it up. This is called the virtual convex probe. All right, and so what the machine is doing here is it's taking these first few crystals on the edge here, and it's sending out the first few scan lines as a sector, just like our sector probe did. And we're getting this fanned out effect. And then everything else is coming straight down, just like it should with the linear array. And then when it gets over to this side, it fires these crystals several more times and starts fanning out to get the wings on our image displayed. So this is how we get that virtual convex image, which gives us the wide bottom and the wide top, the extra wide bottom with this. Okay, and depending on your machine, the bottom will either be straight across or it'll be curved. All right, so the manufacturers decide if this is available to you or not. But the nice thing about the linear array probes is that there's a lot of steering that can be done with these. So we typically use them a lot for vascular exams because we like to have lots of steering available. Okay, that pretty much covers most of the image shapes that we see.
Well, why does it get narrower when we go deeper? Why can't we have the same width with more depth? Because sometimes they get so skinny here.
The linear array probes, yeah, not all of them have that ability to fan out like that. So you end up with what's really, just a big skinny box. Yeah. Yeah. Yeah, it's just simple. Not all manufacturers have built in that ability yet. Yeah.
Is it still firing the same amount of crystals?
Yeah, generally it's firing all of them. Yeah. Yeah, okay. Anna, your question?
I noticed when we were skin, I think it was a vascular study, the tech had, I think he stirred the entire image would go kind of like that to the side.
Mhm.
It was still straight, but he just kind of angled it.
Yeah.
Was that done with the steering?
Mm-hmm. Yeah, that's electronic steering. That's called B steering. So she's saying that she noticed that the image, instead of being a square box underneath the probe, the tech wanted to see something that was maybe, say, over here. Okay? Well, how do we see that with our probe? There might be a mandible or something right here that we can't move our probe beyond. So some of the probes have the capability of using that same electronic steering, the building up of the wavelets into waves, and they can actually steer the image just like that. So instead of having a square image, it's got an image that's kind of moved off to the side. All right? And those of you that were in the lab yesterday, we actually did this, and we were able to see the image swung over to the side like that. Those of you that weren't there yesterday will get to see that today.
What size do you need that for?
Let's say you're doing a carotid artery and you run into the mandible here, and your bifurcation actually happens to be superior to the mandible, but you can't get your probe any farther up because the patient's physical body just won't allow it. You're stuck there. So you can move electronically, you can move your beam farther up.
So would that mean that's like a long picture then, where it goes up like that? You won't be able to get that picture transferred?
Well, what you can do transverse is you just turn your probe sideways and then tilt it. So that will help it. But yeah, there's definitely going to be limitations when you run into things like bones in the way. So this is just a way of getting around it electronically.
Would this affect the quality of the image since it's sending a sound beam like not at 90 degrees, it's going to come this way?
It really shouldn't affect the quality of the image. It really shouldn't. I haven't seen it degrade the images when you do that.
Okay.
Yeah. And when when you use a sector scanner, you're always angling it one way or the other. So, the idea that this would degrade it, I don't think that it will. If it does, it's not much. Yeah.
And what's that called then?
When you shift it like that, well, manufacturers have different terms for it, but typically it's called B steering, because this is our B mode that we're looking at. Our grayscale image is our B mode. Okay, so they're just steering the B mode, is what it is. Yeah. Yeah. Okay. All right, so let's talk about side lobe artifacts, and in our transducers that are made up of multiple small crystals, we call them grading lobe artifacts. Now, we talked about side lobe artifacts with the single crystal transducers. Samantha, can you explain to us what the side lobe artifact was?
Isn't that where whenever we come out and we have to use the
Right. So we create a strong main beam that comes off of our transducer, and then we have these weaker lobes of energy that are coming off to the side, and these are called side lobes. In the multi-wavelet world of these phased array transducers, they call these grading lobes. Okay. I don't know why they decided to give it a different name. It's because you guys just don't have enough to learn as it is. So let's give you one more word to memorize. We're going to call it grading lobes in phased array, and that's one more multiple choice thing that they can put on the exam. Grading lobes are generally caused by when these crystals are hit by an electronic signal. You remember they deform, correct? They're piezoelectric. You hit them with electricity and they'll change shape. It turns out that not all of the shape is just frontwards and backwards. Sometimes they vibrate a little bit to the side. They're not perfect materials, and so they'll expand not only this way, but they'll expand a little bit sideways. Okay, and that's what's going to build up and start creating these grading lobes. All right. So all of these different crystals are firing off, and all of them have this little bit of expansion sideways, and it's going to help to create grading lobes. And so what they discovered is, well, there's something we can do to help diminish these grading lobes, and that is we'll vary the voltage that we hit each crystal with. Okay? So I talked today about using timing on these crystals, or using groups of crystals to change the diameter of the crystal that we're, the effective crystal diameter. Well, if we vary the voltage in each of these so that, let's say, I want to use these 5 crystals in my image right here, okay? We're going to create a sound beam with just those 5. And I'm going to have the biggest voltage hit that center one, okay? We're just talking about the amount of voltage that we're hitting with. And at the same time, I'm going to hit this one with a little bit less voltage, and this one with a little bit less. And then at the same time, I'm going to hit this one with just a small amount of voltage, okay? So we've got tiny voltages out here and a great big voltage in the middle. So what that means is that this piezoelectric crystal is going to expand a little bit. This one's going to expand a great amount. And these two next to it are going to expand somewhere in the middle, little baby bears. All right? So by doing that, by changing this voltage here, we reduce our grating lobes. That's all it's doing. And it still gives us a nice big effective wave. It reduces our grating lobes. And then we call this apodization. All right? So this variation in voltages that we're hitting our crystal with is called apodization. So we're not hitting every single little crystallet with the same amount of energy. We're sometimes hitting it with less. And that reduces grating lobes. So if someone asks you, what is apodization, Stephen, what are you going to tell them?
Used by manufacturers to increase side lobe.
A technique to decrease grating lobes. Yep. Don't call it side lobes, though.
Oh,
They'll get you on that.
single crystal.
Yep. Side lobes are single crystal. Yep.
So they're using the largest signal on the one that's in between others, so this one emitter doesn't have room to expand sideways, is that's what they're hitting? With this biggest signal? Does that have something to do with the location of it?
I honestly don't know if the largest signal is going to be the one in the very center or the ones on the outside. I just know they vary the voltages. Yeah,
Okay.
yeah. They vary the voltages to reduce the grating lobes. That's all I could tell you, to be honest with you. Yep.
And that's all at the same time as the steering and the timing.
Mm-hmm. Yep. So this is all going on at the same time as the electronic steering and the electronic focusing. Yep. So what it comes down to, though, apodization is small variables in voltage to reduce grating lobes. And you're not going to be asked to go in there and figure out what the apodization changes should be for any given transducer. We're going to let the guys that built it do that. But we do have to know what apodization is, just as another word for our vocabulary.
But even back in the book definition, includes grading and side lobes.
Yeah. There are some errors in the book. The book is probably correct. I'll say this. The book is probably correct on that. These can be called side lobes or grating lobes. But for the ARDMS registry exam, grating lobes occurred on phased array transducers and side lobes occur on single crystal. Okay? Single crystal side lobes, grating arrays,
It doesn't seem like
phased array.
do the apodization of single crystal.
Right, you can't do that on a single crystal. Right. Right, you can't do apodization on a single crystal. All right.
Is that crystal a much bigger crystal on the single one than these are?
Yeah. Yeah, these, because we're typically going to be scanning at, for an abdominal scan, we're going to be scanning somewhere down at about 10 centimeters depth, right? Okay. So we need to use, for 10 centimeters depth, we're going to have a crystal diameter of somewhere around, what is it, 2 to 4 millimeters is going to have to be our crystal diameter for a single crystal. And these little crystallets in a phased array are less than a millimeter. So you're going to have to use multiple crystals in order to get a focal zone down here at 10 centimeters. Right. No, it's not. Yeah, it's not huge, but it's, you know, because when we look at our curved array transducer, or our think of a linear array transducer is about that wide, right? And I don't know exactly what measurement that is, 1.5 inches, 2 inches. Well, there's 250 crystals within there, so it's definitely, they're definitely smaller than 2 to 4 millimeters, but yeah. All right. So let's talk a little bit now about annular array transducers. Okay, so if we have a crystal and we're going to make our transducer out of multiple concentric crystals like that, all right? And so this one is actually facing out towards you. I have a hard time drawing it on the board so it's facing down like I do my usual crystals. But you could think of it as, we'll try to point it down. And I've got my very center one here. And then outside of it, I've got another group and then another group. Maybe I should do this in color, different colors. Okay. So we take this and we turn it down, and this is what we end up with. All right, the idea behind a annular array crystal was that you can look at this and you can see that if we fire off all of these circular things at once, we're going to have a natural focused ultrasound beam at some point down here is our NZL. But now if I take this and I attach wires to each of the outer I can actually change where my focus is with this annular array by changing the timing of this. So if I fire off this outer one first, and then wait and fire this one, and wait and fire that one, and then fire the center one last, I'm going to get again a focused beam. And so instead of having my natural focus down here, I've now raised it up to this point. And it'll focus there and then bend out. Okay? And so this was the first attempt at electronically focusing an array. Okay, we weren't able to steer these because they were still essentially in a single crystal transducer that we just divided up into many circles, is what we've done here. But now we can electronically focus it either down here or up here by changing the timing pattern to the different crystals. All right. The nice thing about this particular type of transducer is, okay, you can imagine this round transducer being tipped over. Both our lateral resolution and our elevational resolution always change to the same point. Okay? That was the good thing about it, is that an annular array transducer had the ability to focus in the lateral and the elevational plane simultaneously. Okay, so when we were in the labs and we were playing with lateral resolution, and the next week we looked at elevational resolution, we saw that they didn't always correlate. In fact, you could adjust the lateral resolution with our new transducers, but you never could adjust the elevational plane resolution, except for that one probe, which didn't actually work very well anyhow. So using annular arrays, we were able to change the focus electronically. Now these still had to be swept back and forth, so they were still mechanical. They were kind of a hybrid mechanical electrical electronic array probe. But you could get one scan line out of it, and you could focus that scan line at different points. Well, that's the idea behind the annular array probe. And, oops. And that's the, so when we look at these, they would take these and they'd turn them up, and you'd use the firing patterns to change the focus. Okay. Everyone has a good idea of what an annular array probe is? It worked like a single crystal transducer in that you still had to wobble it back and forth. But it had the advantage of being electronically focused. And it still has the advantage of being the only type of probe that is electronically focused in the lateral and elevational planes at the same time. Okay. I know, Stephen, you've been telling us about these probes that you've seen that had thousands of crystals on them, and they're three-dimensional or two-dimensional probes. Those will be able to focus in the elevational plane also. But we're still waiting to see them working on a daily basis. Yeah. All right. So before we wrap up, do we have any questions about what we covered today? Is everything clear? How about things that we've covered before?
So, how many types of probes are there? I know there's based on only single crystal.
Okay.
The linear array, phase array, and the fusion array. Those ones we need to know.
Yeah. So when you think of the linear array probes, I want you to remember the sequential linear array probes and the
That's right.
the segmental linear array probes. Remember what those were? And then phased array. Every probe we use in our lab today, if we're not on that old machine, is a phased array probe. If we're on that 1980 machine, yeah, we can get some sequential and those and single crystal arrays. But just about every probe that you guys will be using in your scan labs at clinicals are phased array probes.
So phase array could be linear.
Yeah,
too.
yeah. The linear array probes can be phased array. The original kind were the sequential, then they went to segmental. Now they're at phased array. Yeah, and they're all linear array probes. We can create different types of images with those linear array probes. We can get the little box image. We can get the box image with they call that the trapezoidal. If we're using complete electronic steering, we can get what we call generally the vector image or sector image with the phased array probes. Okay? And then the curved array is also a phased array probe. Okay? So this is kind of a quick synopsis of the different image types that you can create. I can't think of any others. Can anyone else? All right. All right, so the little index cards, I want you to fill that out over the course of this week, and then Monday, give that back to me. It can be anonymous, but I want you to have something written on there that you want a further in-depth explanation on, okay? And so I will pick up your index cards on Monday. Now, some of you should have index cards from last week that I'll be picking up in the lab this afternoon, all right?